these are the formulas we have from D operators. And when you solve differential equations, you know that the complete primitive or the general solution will be a sum of two expressions. This is the complete, this is the complementary function, this is the particular integral. Or in engineering point of view, this should be what? This one. This is a forced response. What is this? That is a transient response, which lasts only for a small period of time. That's what transient means. But in the point of mathematics, like you call it as complementary function, this is particular integral. Now, if you take this differential equation, particular integral totally depends on this one, and the complementary function depends on the shape of the differential equation, the left-hand side of the differential equation. It doesn't matter what you have here. Okay. So, when you find the complementary function, if you try the usual trial solution, if you get two distinct solutions, you write the solution like this. If you get coincident roots like lambda 1, lambda 1, right, then you write it like this. To come up with two independent functions, you have to do it like this. That also comes from operator theory. And this one, when lambda is in the form of alpha plus or minus psi beta. If you get complex roots, then you have to write the answer like this. We went through that in the previous chapter. I just want to recall what we did in the previous chapter. Now, let's do examples. Now, first we need to find the complementary function. It comes from complete, right? So this letter should be E. We'll first find this. So how can you do that? We consider the homogeneous equation for this purpose. Homogeneous means the right-hand side is 0. Right? Now, what would you try? You try y equals k e to the power lambda x. Why would you try this? Because this is the eigenfunction of the derivative operator. So that's why we try that. Now we find dy by dx. And again, by differentiating this, you can find the second derivative. You get k lambda squared e to the power lambda x. Now, plug in these things in the differential equation. Now, this becomes what? Sorry, I have made a little mistake. I have to consider I told it's a homogeneous function. Sorry, homogeneous equation, where the right-hand side is equal to 0. I told it and wrote something else. This should be 0. Now you plug in these guys in the equation. So you have k lambda squared e to the power lambda x. Then you have 3 times this. Sorry. 3 times k lambda. Here you have 2 times k e lambda x. Right? Now you can pull out e to the power lambda x as well as k. So you will end up with lambda squared plus 3 lambda plus 2. Now here when you come up with this trial solution, even k is 0, k being equal to 0 is acceptable. Right? Because when k is 0, this is 0. Look, 0 plus 0 plus 0. Look, 0 plus 0 plus 0 is 0. Because when y is 0, its derivative is 0. So that's also acceptable, but it's a trivial solution. Trivial means what? It's useless. Therefore, if you want to get something useful, you have to force k to be non-zero. So if you do that, k is non-zero. This is a product. E to the power lambda x will never be 0. Therefore, you get this is equal to 0. I mean, you can solve this. I'll write the answers. Lambda is -1, -2. So when you have distinct solutions for lambda, you write the answer in this form, where k1 and k2 are the arbitrary constants. We saw those things in the previous chapter. When it's the second order, you get two arbitrary constants. Now I can write yc straight away. k1, right, e to the power -1 x plus k2 e to the power -2x. So that's it. Now we will go for particular integral. In the previous chapter, we found the particular integral by the method of undetermined coefficients. But today, we are going to do it in a different way. We are going to use D operators. This is just a piece of cake, so easy, right? So this is what we have to do. This is a differential equation you have. Right. So write this in terms of D operators. Now D means what? D over dx. Here this is D squared. So you can write it like this. D squared y 3dy plus 2y is equal to e to the power minus 3x. Now you can pull out y from this side. Now you can find y. Here you can just play with these things. I told you the operator theory allows you to do the algebra involved with these D operators freely. In the previous chapter, we almost violated all rules of algebra, right? Now, what should you do? Now, this is FD, this is alpha. Alpha is -3. So plug in -3 for D. In the sign, this is not a sign function, so you have to do it like this. -3. This is 9, this is -9, this is 2. So this is a particular integral, yp, which is a solution to the differential equation. Now you can write the general solution. In mathematics, sometimes you call the general solution as what? Complete primitive. Right? In mathematics, usually this is okay. Let me write the full answer. The general solution, or the complete primitive. In the context of mathematics, you call it as complete primitive. Is y is equal to yc plus yp. You know the physical significance of these guys, right? We saw it earlier. So y is equal to, this is yc, this is yp. Okay. So that's how you do it. Now, in mathematics, this is called the complete primitive. This is complementary function. This is particular integral. But in the context of engineering, if you take the physical significance of the differential equation into account, you call this as what? Transient response. It lasts for a little while. P is the forced response. Forced means the outside force. It may be an electromotive force. It may be just a force to the system. So because of that, the effect due to that external force is called what? Forced response. Okay. But in the context of mathematics, you call it as complementary function, particular integral, and this one complete primitive. You can use either way. In the context of engineering, in the context of engineering or dynamical systems, you call it as general solution. This is transient response. This is forced response. Okay.